Okay, good afternoon, everyone. Let's get started. So at the end of last lecture, we talked about the more general definition of probability space, right? So a little bit different from, it might be a little bit different from what you have learned before. We're trying to inject some like a measurement or measure theory based probability definition. But again, don't worry, we won't go very deep about measure theory. I just want to give you a concept. So the rigorous mathematical framework to describe probabilities are based on measure theory. So when we talk about the probabilistic model, actually it is always has some underlying triplet, right? We got the sample space, right? Or the sample space is sometimes it's called universal set, which contains all the basic unit or basic outcome of your random experiment. Like if you toss a coin, then the sample outcome might just be heads up and the tails up, right? If you roll a die, right, and the sample outcome might be 6 points, 1 to 6, right? And then this F is often called events. So you can view it as sets of a set of sets, right? Each element in F is a subset from omega. So so basically, we use a set of samples to represent random event, right? Like if you roll a die, like you roll a die, like if I want to define an event that my point is at least 4, the actual is represented by a set, which is 4, 5, 6, right? So actually, in mathematical word, suppose this is omega, right? You got many samples in your universal set, where you can pick up an arbitrary subset of omega to construct an event. So this is one element in your event space, right? Of course, you can pick up any collection of events which you're interested in to construct your so-called event space, right? But as we mentioned before, you cannot construct arbitrary set of the events in this omega to construct F. If doing that is allowed, if allow us to doing that, it will incur some paradox, right? So in practice, in theory, if you want to make your F to be consistent, won't be any contradictory results. F is usually constructed as a so-called sigma algebra, right? So it's sigma algebra is a definition of set of sets. So basically, it is closed under completion. It should include empty set, and also it is closed under countable union. Well, you don't need to recite that. I just recite it for you. And once you define an even space, you need to give a probability measure function which assign the probability for each event in this even space F. So that's why this measurement, this probability measurement is essentially a mapping from the even space to a number between 0 to 1. Right? So all those are defined very naturally, and also to be rigorous enough so that you can construct all kinds of like upper level components for probabilistic reasoning. Right? But if we just rely on this triplet to define our probabilistic models, it will be not very convenient because practice, like different random experiments are very different, right? We don't want to, we want to find out some commonalities out of those all different kinds of probabilistic models. That's why people trying to come out another kind of mapping, right? Why not just map those events or those samples to numbers, right? Because in the abstractive world, like mathematicians are used to deal with all kinds of numbers, real numbers, integers, natural numbers, or even complex numbers, right? Because we have a bunch of like very good and refined theory to characterize the numbers. So that's why people come out the so-called definition as random variable, right? So random variable is mapping from your sample space to another, to another measurable or metric space. Well, but usually when we talk about random variable, we're talking about the mapped space will be real space and associated with the sigma algebra define a real space. In this case, is often called Fourier set. But what is Fourier set? You can roughly view it as countable unions of all intervals in the real space. But if it's two-dimensional space, three-dimensional space, you can view it as countable unions of all the rectangles and cubics. But they can be shown that Fourier space is kind of sigma algebra. So, and based on so that's why when we talk about essence of a random variable, it is essentially a function. It's a mapping. It's not random. It's also not a variable. Right? The map any samples which essentially is random because it comes out from some random experiments to some number in the space, in abstractive space, right? So, but if you want to define the random variable, right, we want this random variable, this function, to be measurable, meaning that, okay, if I can pick up the range of the random variable values inside this Fourier set, it can map back to some valid event in my probability space. That's called measurable. But again, I just give you the hint. I just give you some kind of concept. You don't need to memorize this. Just feel like how they kind of like define such kind of a construction, right? And why people want to construct random variable mapping? That means if I want to research the chance or the relationship between different type of events, I could just look at the range that random variable values can take. For example, for one-dimensional random variable, right, that is just a real number, right? We are particularly interested in a particular type of range that if the output or value of the random variable is less than or equal to some particular real value x, this small x. Right? So, and this inequality, so people usually represent as a function of the sample from the sample space. This guy less than or equal to x, this small x is a real number, is just to tell you, this represents an event in the even space such that, that the random variable's output is less than or equal to x, right? This guy belongs to the even space. So we are particularly interested in what is the probability measure over this event, right? And of course, for convenience, you don't want to explicitly write out this event, this set. So that's why usually when we look at this definition, we just look at, okay, this probability of a big X less than or equal to X. But you should understand what's the underlying meaning of that, right? So, and of course, this event, the probability of this event actually varies along with the small x, right? Because the small x defines the range where the value of the random variable falls in. You change the x, you actually change the range, and also you change the event, also change the probability measure on that event. Okay, so you can define this is essentially a function, right? It's a function between x to the probability measure, which is between 0 and 1, right? Does it make sense? Right? Just interrupt me at any time if you feel uncomfortable, feel unclear. Don't be shy. We have a small class. Don't be shy. Yeah. So in this way, by leveraging the definition of random variable, we can define the so-called cumulative distribution function. Cumulative distribution function. And the cumulative distribution function actually has several nice properties, which you have seen in your textbook before, right? So first, f, big F is guaranteed to be monotonically increasing. And F is right continuous. Okay? So meaning that if this is a function, right? If you converge, this is x, right? If you try to calculate the limit of this function from the right to x, and it converges to f of x itself, right? It doesn't necessarily to be left continuous, right? Again, this proof, if you really consider the underlying probability structure, that it's not very easy to show that, okay? And we can also show that when x takes negative, take limit at negative infinity, then this cumulative distribution function 0. When x takes to positive infinity, then this cumulative distribution function is 1, right? So all sounds reasonable because it's unlikely that for any value of the random variable, it will be less than minus infinity, right? And for any output of for any value of x, it will be sure that it will be less than or equal to positive infinity. Oh, by the way, you don't need to make any notes. These are shared, in the website. You can download the PDF, right? And also, if you think, okay, my notes on that, you can just watch them on a lecture video. Okay, and then these are this probability cumulative density function are talking about any types of value of the random variables, like x to be real value random variable. You can also define this as discrete value random variable. But in particular for discrete random variable, right? Discrete value of the random variable x, right? We can define the so-called probability mass function. Right? But that means your random variable. That means the probability that your random variable's output takes a particular value. Like for example, you can define your random variable mapping from some random experiments outcomes to say 1, 2, 3. Like we will have 3 outcomes, right? So and then you can ask, okay, what is the probability measure that this corresponding event happens? That means, okay, what is the event? What is probability event that your random variables output all equals to this particular discrete value, right? And it's this is called probability mass function, right? So you can also define your cumulative distribution function based on your probability mass function. So if you want to look at the probability that of the event that corresponds to your random variable x, big X, less than or equal to the small x, then you just sum up the probability mass at all the random variables choice values who is less than or equal to x. So if your random variable x take the value to be continuous and real value, right? And we can naturally consider like why not we just take a derivative with respect to x, right? As we just mentioned, right? This guy is a right continuous, right? We can still take the derivative, but in this way you can view this as a right derivative, right? It's not a full derivative, right? Because you have to compute the derivative from right hand side. And then we call the derivative of the cumulative function as the probability density function. That's the one we commonly use and use very, very often. And then we can re-express the cumulative distribution function as an integral of the density function, right? Yeah, this guy is just the derivative of f of x. So of course, f of x will be integral from negative infinity to x, right? With respect to p of with respect to density function, and because the f evaluated at negative infinity is simple to 0, right? So we can just write it as an integral. Does it make sense? I'm just repeating what you have learned before. So here we can take a look at some example. I believe this appears in your previous text before, right? So I'll know that if we talk about a uniform random variable, right? I mean, it is uniformly distributed between 0 and 1. This is standard uniform distribution, right? We know its probability density will be something like this, right? So this is 0, this is 1, right? And outside of this range 0 and 1, right? The density is simply 0, right? And between 0 and 1, the density is simply 1, right? And based upon that, we can use the integral to compute the accumulated probability of accumulated distribution function, right? So it's typical, it's something like this, right? Between 0, so it's something like that. Between 0 and 1 is just a line, right? And after 1, you know that the cumulative functions has already been 1, right? So just being 1. Okay, transformation of random variable. So suppose we got a random variable x, and also we got a random variable y, but there's a relationship between x and y, right? That means we can represent x, y as a function of x. And here we assume that x and y are of the same dimension. Right? If it's not same dimension, we cannot use this transformation formula. So like if x is a 3-dimensional vector, then y must be 3-dimensional vector as well. Right? So and naturally we want to know, okay, if suppose we know the density of x is p of x, right? And we naturally want to know what is the density for y. So this is there's a simple formula for this, right? If you want to compute the density of y, right? You just represent x in terms of y. So that's why it's called f inverse y, right? And plug it into the density function of x, right? And then multiply the absolute value of the determinant of the Jacobian. So basically this one is absolute value of determinant of dx over dy. Right? So if you want to get density of y, right? If you want to get density function of y, how you do that? Like you got density function of x, right? Suppose this is just s cubic plus 1, right? Of course, it's not valid density function, but I just use it for wild example. Right? If you know y say equals to 2x, right? So you're gonna represent x equals to, in terms of y, so it's y over 2, and then you plug in that to get this, right? So this one will become half y squared plus 1, right? And then you multiply the Jacobian, that means your gradient of x with respect to y, right? You calculate Jacobian and calculate determinant of Jacobian and take absolute value, multiply, you get density 1. This is where well-known formula, and it is actually very useful for the so-called gradient flow or normalization flow in the probabilistic inference. because the idea of this type of inference is that, okay, I want to approximate a very complicated posterior distribution. And how can I do that? I'm going to introduce a y, right? I'm going to introduce another random variable y. I say it is sampled from some standard normal distribution. It's very simple, but I assume that the posterior of x can be approximated by a series of very complicated transformation of this standard normal distribution. Then the problem is that, okay, how can I estimate the parameters of these transformations? And there's a framework, it's called a variational framework, which is essentially to minimize or the distance, roughly speaking, distance between the target posterior and the approximate posterior. And of course, if you want to know what is the density of a random variable after its transformation, right, you have to apply this formula again and again. That's why this formula is very useful. But again, you don't need to memorize that. When you use it, you just Google it. Okay. And here I just mentioned that how is this arrived? How is this derived? Right? How do you show this? Right? So so the basic idea is that on a infinitesimal change of x, like this is suppose this is the space where x resides, right? At any particular x, right? We know that if we perturbate x with dx, right? So sorry. At this position x, if you perturbate with dx, well, you can consider like you have a very small cubic. Right? So the basic principle is that, okay, my density for x multiplying with this cubic determined by dx. Dx is infinitesimal change of x, right? Should be the same of my density with y, right? And multiply the volume determined by the infinitesimal change of y. Okay. So it's like, okay, I change x a little bit, right? I do some transformation of x. I put y in another coordinate system, right? And then at two places x and the corresponding y, like if I change them very mildly, so I got two small cubic, and I should ensure that my probability measurement on these two cubics are the same. And when this cubic, right, when this cubics are very small, like you can roughly think, okay, the density, the probability density on this cubic is the same, right? So that's the whole probability measurement over this cubic is density multiplying the volume of the cubic. Right? And similarly, in the white space, right? In the white space, in that the infinitesimal change of y will determine another cubic, and you want that your probability measurement over this cubic, those y cubic, should be the same. Right? And then you know that okay, we know this density function for x, right? And if we want to get the density for y, right, we need to know the ratio between the volume over dx and volume over dy, right? That's where this absolute value of the determinant of Jacobian come from. They can show that in general, the ratio between the two volumes, the volumes of two cubic is this guy. Does it make sense? Right. Any questions? I don't want the class to be very quiet, right? Just my solo show. Let me know if you have any question. I give you the hint, and if you're You can try to use like two-dimensional case. This is fairly easy to show it with like two-dimensional case, like or three-dimensional case. You can show that as well, and then it can be extended to a higher arbitrary n-dimensional case. Everyone's good. Okay. So now we move to several important definitions regarding random variable, right? The first one is the so-called expectation or mean, right? Everyone knows that definition. So basically, it tells on average what's the value this random variable can take, right? And for continuous random variable, the expectation is defined as this integral, right? So it's the integral of the x itself times the density of x, right, in the range from -infinity to +infinity. Right? And if your random variable x is discrete, right, it means that it takes discrete value. That just means a weighted summation of all possible values that random variable x can take, and weighted by the probability mass on each value, right? But if we take a more general view, like we can view like, okay, summation integral essentially is a general summation, right? So it can always be written as the integral of x and density of x. And there are several like very important property of the expectation. I think the most useful property is called linearity, right? So basically, if we have an x and y, well, two random variables, right? It doesn't matter if x and y are dependent or independent, correlated, uncorrelated. Their expectation, the expectation of their linear combination, like x plus by, is simply linear combination of their respective expectation. Now, this is a very useful property. Right? And it extends to a list of random variables x1, x2 to xn. Suppose they're linearly combined with constants a1 to an, so their expectation is equal to the linear combination with the expectation of each random variable. And this can also be extended for expectation of random of a function of random variable. Right? Suppose we got a continuous function, right? And then if we want to compute the expectation of g of x, right? So remember, x is a random variable, then g of x will also be a random variable, right? So if you want to compute the expectation of g of x, you can just integral the density of x with g of x, rather than you will it as some function y, right? You get the density of y first and then calculate expectation of y. That usually will be much more complex. And in discrete case, the same thing, right? You just evaluate g of x, all discrete values that x can take, and do the weighted summation according to the mass, probability mass on each xi. Okay, variance. Okay. The variance of the random variable x is defined as follows, right? So you calculate the square difference between x and its expectation. And this one, of course, is a random variable. So you take expectation again. That is where you get the variance. Any question? And you can also show that the variance of x equal to the expectation of x squared subtracted by square of the expectation. Is really straightforward to show this, right? So can we like variance as a measurement of the spread of distribution. If a random variable is really very, very random in that it has a large chance to go far beyond from the mean, right? That means okay, its variance is quite large, right? And if the random variable is its value most likely to take to be close to the mean, then the variance is small. So the variance is a very, very important metric to show the stableness of the random events happen on the line. Right? Another commonly used property is called standard deviation. Standard deviation is simply the square root of the variance. So this one, because it has the same kind of skew with the mean, right? So you can view like, okay, this is your expectation, right? The standard deviation is just tell you, okay, on average, how far away your random variable takes value, different from the expectation. And the variance is actually the square of this difference. The expectation of the square of this difference. Any questions so far? Okay, great. So now let us look at a few examples. The first, and also for most important continuous variable distribution is normal distribution. I believe everyone has seen it before, right? So normal distribution is usually determined by two parameters. One is called mean parameters, one is called standard deviation. Right? So basically means if a random variable follows a normal distribution, all we need is to know what is mean and what is the variance or what is standard deviation, and you know everything about this random variable, everything about this distribution. Right? So the density function of a normal distribution random variable, a normally distributed random variable, is like this, right? So this form, I'll suggest you to memorize it because you're gonna use it so often. Right? So it's an exponential form, right? So in an exponent, it is minus square difference between x and the mean and divided by two times variance, right? And here, this guy 1 over square root 2 pi sigma is a normalization factor, right? It is ensure that, okay, when I integral my density function from minus infinity to positive infinity, it is 1, right? And you can also show that with this definition, right? With this definition of the density function, if you take expectation with respect to x and f of x, you'll give mu. And if you calculate the variance, like according to the formula which is mentioned, it'll give you sigma squared. Okay, any questions so far? Okay, so now let us talk about joint distribution, right? Previously, when we talk about two events A and B, we know that it's two sets, right? We can talk about the probability of intersections of two events, A intersection with B, right? So we call this probability as the joint probability of A and B. So in our notation, we often write it as PA and comma B, right? And be careful. This is actually talks about the intersection of the probability of the probability of intersection between A and B, right? It is not the probability of union of A and B. Okay? And this one actually is bigger than probability of A and then probability of B as probability of A intersection with B. So we're going to extend the definition of joint distribution from the events to random variables. Suppose we got two random variables x and y, right? Then we can define the joint cumulative distribution function. Right? So this is done as follows, right? So it's function of x and y, right? So it is probability that the intersection of two events, right? One event is determined by x, big X less than or equal to x, and second event is determined by big Y less than or equal to small y, right? Remember, this guy corresponds to one particular event, right? And this guy corresponds to another particular event, right? They actually kind of associate two probability space, right? And because this joint probability is determined by both x, y, so that's why we view this joint accumulated distribution is a function of x, small x, and small y. And then we can take the derivative, take the partial derivative over x and y, so get the so-called joint density. That's where the definition of joint density come from. And then we can recover the cumulative distribution function by just integrate the joint density, right, with respect to both input variables, right, x and t. That's the standard definition of the joint probability density. And with the joint probability density, then we can talk about what is the marginal density, right? Those are all like calculus, right? So if we want to get the marginal density of a single random variable x, right, we just do an integral over the joint density with respect to another variable. Okay. If you want to get p of x, it's just integrate p of x and y with respect to y. Okay. If you want to get p of y, you just integrate pxy with respect to x. If it is discrete, then you just sum out the values that all y can take. Right? So here, it's just one very simple example to reinforce our definition. Right? So we got two Bernoulli random variable. We got code, or we didn't got code, right? So it takes value 1 or 0. And another random variable r represents you got running nodes or no random nodes, 1 or 0, right? So the joint probability mass function is like this, right? So each entry in this table represents the joint probability that your r and c take particular values, right? So based upon that, we can compute the marginal probability for r and for c, right? For example, if I want to compute the marginal probability for r, so what should we do? Yes, exactly right. That's what we did, right? So for r equals to 0, right? So we know that we need to sum out all possible values that c can take, right? So take the first row, so we get 0.50 plus 0.05. That's where we get 0.55, right? For r equals to 1, we just marginalize out the c values when r takes 1, right? Which is 0.20 plus 0.25, which is 0.45. Okay. Similarly, you can compute a marginal probability for c, right? So just sum up over the columns. Okay, so based on the joint density and the marginal density, we then can define the so-called condition density. So what is condition density? We define that the condition density of x given the random variable y takes the value small y as the joint density of x and y divided by the marginal density of y. So this one, remember, don't get confused. This is just tell you that this guy is big X equals to small x, big Y equals to small y, and divided by big Y equals to small. Okay. And this one is just tell you, okay, what is the probability density that when big X equals to X, given that big Y equals to small y. Okay. So for just for notation convenience, we just ignore the random variable, the big X and big Y. And based upon the same probability table, right, we can compute the conditional probability when say variable take different values, conditional the case that R takes different values, right? For example, if I want to compute the conditional probability that say takes 0, given that R takes 0, right? So we need to first compute the joint density that say equals to 0 and R equals to 0, which is what? This one, right? Someone has pointed out, it's 0.5, right? Then we need to divide it by the marginal probability that R takes 0, which is 0.55, right? It's here, right? That's how we get the conditional probability. And similarly, you can compute the conditional probability that say equals to 1, conditional R equals to 1. I'm not going to repeat this. Okay. Okay, independent random variable. We call two random variables X and Y are independent if their joint density equals to the product of their marginal densities. We can also view this as from the perspective of the cumulative distribution function. You'll see that the cumulative distribution function of X and Y equals to the marginal cumulative density function, or cumulative function for X times marginal cumulative function for Y. Okay. They're actually they're same, right? Because if you integrate them both on both sides, you immediately get this. Does it make sense? And then we can define the so-called conditional expectation. Right? So we know that expectation of any random variable X, right, is an integral of X multiplied with the density function of X dx, right? And the conditional expectation is very simple. You just replace the density function with the conditional density function. So when we say, okay, the expectation of X conditional on the random variable Y takes the value small y, it will simply be this integration. This tells you, okay, when your random variable Y takes a particular value, what is the conditional expectation of X? So now I want to ask a question. What if I want to ask you to look at this one? Is this a constant? Is this constant or random variable? Why? Yes, very, very important. Right? So be careful. This guy is a random variable. So this guy essentially is a function of y. Why I can say this, right? So you can see that for a particular choice of big Y, like say small y here, you got the conditional expectation for X, right? But if you choose the big Y values to be another, like Y hat, you got another conditional expectation of X, right? So actually this conditional expectation varies with the value of the random variable Y. It depends on the random variable Y. That's why we should view it as a function of random variable Y. Does it make sense? Okay. And there's a famous conclusion that if you further take the expectation over the conditional expectation to give you the expectation of X, not conditional on any other random variables. I guess in your homework 0, I'm showing that this, right? Okay, just to remind it. And discrete case, well, you can view it the same, right? Except that you're gonna replace the integral by the summation. And we can also consider like expectation of the product of two random variables. So if you want to like look at the random variable expectation of X times Y, right? So just do the integration of XY times the joint density of XY, right? So actually this can be extended for even more general case, like if I want to look at the expectation of a function of two random variables, right? You just replace XY by this function. Okay. Then that's it. Okay. Our next important concept is called covariance. So covariance of two random variables are defined as follows. It is an expectation of the product between X subtracted by mean of X and Y subtracted by mean of Y. So you can, we will like X subtracted by mu of X is like centered X, right? Because X has a mean, mu X, you subtract the X by mu X is a centered X. And similarly, the centered Y, and they just take expectation of the product between centered X and centered Y. You can also show that this covariance equals to expectation of the product X and Y subtracted by the product of the expectation of X and expectation of Y. So the covariance is a very commonly used measurement about how much variable X and Y like co-change. So you can imagine that, okay, if X change much and Y also change much, then their covariance is large. If X change much but Y change little, then the covariance is small. Right? And if you further normalize the covariance, right, by the standard deviation of X and Y, like that is the covariance of XY divided by the standard deviation X and standard deviation Y. This is called correlation. And correlation can be also defined in this way, right? It's kind of like, okay, a centered X and then divided by my standard deviation. Right? It's kind of like normalize my random variable X, normalize my random variable Y, and see how they will change, right, in the normalized space. So any questions so far about this definition? Okay. If two random variables are independent, then their covariance is simply 0. Okay. It's very easy to show that. Okay. I will leave it as an exercise for you to show this, right? So this actually tells us that if random variables are independent, that means they are uncorrelated. However, I want to ask, if two random variables are correlated, are uncorrelated, are they independent? Any thoughts? Yes, exactly. This is very, very important. So be careful. Like you got 0 covariance, which doesn't mean like these two random variables are independent. But of course, if two random variables are independent, they must be uncorrelated, meaning their covariance must be 0. Okay. So this will their equivalence happens only in the special cases. Like for example, if your random variables are Gaussian random variables, and then correlation is equivalent to independence. Right? However, for other type of random variable, like for example, they might have some like harder independence, and then the covariance or correlation doesn't exclude their even higher order dependencies that does not derive that they're independent. So here are the some kind of statement like independence. You can from independence conclude that okay, the two random variables are uncorrelated. However, if they are uncorrelated, that doesn't necessarily mean like they're independent. Okay, any questions so far? Okay, great. Yeah, this is a quick review of all the very fundamental concepts about probabilities, right? And also in general, when we define random variable, what kind of properties, what kind of important properties we must take care of, like what is expectation, what is variance, what is the joint density, what is the marginal density, what is conditional expectation, what is conditional variance, what is conditional independence, all kinds of stuff, right? So this is very, very fundamental, but very, very important. That's why we kind of spent a while to talk about those, right? So next, we're going to start with basic probability distribution, right? So as we mentioned, right, we're talking about probabilistic learning, right? Probabilistic learning is built upon like all kinds of probabilistic models. Like how do you design a probabilistic model? And it's like build a house, right? It's like build any building one, right? And to construct such a building, you need some basic units, right? You need bricks, you need you need some frames, you need all kinds of basic stuff, right? And in the probability learning world, those basic stuff are a variety of probability distributions, right? So if people in this area are taking advantage of those commonly used classical probability distributions, which are well studied by pioneer researchers, especially in statistics. We use them as the basic block then to construct complicated models. Like sometimes, like for the need, right, people like just invent new probability distributions. For example, I think a few years ago, there's one particular type of models which is called a categorical model or a concrete model. You can view this continuous relaxation of categorical variable. This is the motivation is to make the categorical learning of categorical distribution easier with back propagation. Then people develop the so-called continuous relaxation of the categorical distribution, which is called concrete distribution. But anyway, we need to start with the basic probability distributions. So we're going to cover a bunch of like very common used, very important distributions. Again, we're not going to prove why their mean is like that, where their variance is like that. We just list why what does this probability distribution do, right? So what can it be used for, and what's nice properties it have, so that we can leverage them in our probability model. So here's the outline. We're gonna quickly review what is the maximum likelihood estimation, what is maximum A+2 estimation. I believe most of you have heard this before, right? Then we're gonna go through a bunch of probability distributions. Part of them you might have seen them before, like binomial distribution, multinomial distribution, beta distribution, right? No, the Bernoulli distribution. But some of them you might have never heard of that, like beta distribution, like Dirichlet distribution. And Gaussian distribution, right? We're going to extend Gaussian distribution to multivariate Gaussian distribution, which is really the useful thing and very common in machine learning world. And then we extend to the so-called student T distribution, in the multivariate student T distribution. Right? And then we're going to talk about like inverse gamma distribution, or gamma distribution, Wishart distribution, inverse Wishart distribution, which are often used to model some parameter of the Gaussian distributions. For example, when we talk about Gaussian distribution, we might talk about the mean and the variance. Right? And what if I want to place a prior distribution over the variance? Right? You can use gamma distribution. And sometimes if you talk about, if you want to use like multivariate Gaussian distribution, right, then you got covariance matrix, right? What if I want to place a prior over the covariance matrix for a Gaussian distribution? We can use the so-called Wishart distribution, because Wishart distribution guarantees to give you a positive, definite sample of the positive definite sample of the covariance of the matrix, which you can use it as a covariance matrix for a multivariate Gaussian distribution. Okay. So what is maximal likelihood estimation, right? In general, suppose we got distribution. Okay, we got distribution X is the samples of this distribution, right? And theta is actually the parameters which are unknown. I suppose you have observed some samples, right? And you believe, okay, these samples follow some Gaussian distribution. And then the parameters of this Gaussian distribution, oops. The parameters of this Gaussian distribution will be mean and variance, which are theta here. Okay. And then suppose we have a, oops, sorry, I don't know why my pen doesn't work. Oh, okay. Suppose we have observed a set of independent and identically distributed random variables from the distribution, okay? And we can denote these observations by x1 to xn, right? The question is, how can we estimate the unknown parameters data from your observed data D? Okay. It's called a parameter estimation problem, right? So one commonly used framework is called a maximum likelihood estimation. Right? So what is maximum likelihood estimation? It's based on the intuition that, okay, the samples, when you collect them, it's because it has high chance to appear or high likelihood to appear. So you believe that under the distribution parameterized the theta, you got a high chance to sample those observations. In other words, it's unlikely that you observe a rare event, a low likelihood, a low chance event to happen. Right? That's why we want to maximize the likelihood according to the distribution, so that under this optimal parameters, those observations has the largest chance to show up. Right. So when we directly maximize the product of the likelihood of n observations, this is usually numerically unstable. Why? Because each one can be very small, right? If it is between 0 and 1, right? So a more stable approach is that, okay, we're gonna take a logarithm, right? We can take a logarithm over them. It won't change the maximum. But you take a logarithm, your product becomes summation. And inside each product is a log likelihood of each observation xi given your parameter theta, right? And usually it will be much easier to calculate and optimize, right? So this is called maximum likelihood estimation, right? So but when in the probabilistic framework, right, we talk we mentioned our philosophy that, okay, everything is a random variable, right? So that means the unknown distribution parameter theta, we also can view it as a random variable, meaning that, okay, we assume some prior distribution over theta as well. So in that case, we want to account for the prior knowledge. How can we do that? We now maximize the joint probability, right? The prior of the theta multiply given theta the likelihood of the observations. If you're doing maximization over the joint probability, this is called a map estimation. Does it make sense? right? And again, we don't want to deal with a long chain of products, so we want to take a logarithm so that our maximization is over the log prior plus the summation of the log likelihood over every observation. Right? And here, this log prior in a non-Bayesian view is often corresponding to the so-called regularization. For example, if you place theta as the standard normal prior, right? This guy actually corresponds to the L2 regularization. Any questions so far? I assume like this is everyone has heard this before, right? There are not too much things to talk about. We just review this classical framework. Right? However, like although like MLE or MAP is kind of like frequently used, right? And people are trying to build connection between Bayesian and non-Bayesian approaches through MLE, MAP, right? But this is not true Bayesian guy will like. Right? It's not ideal from Bayesian perspective, from probabilistic perspective, because remember, we want in the Bayesian world, we want not only a point estimation, we want some distribution, right? Because distribution includes not only one point, includes all possible points, and also their distribution, right? Their uncertain information. Right? This is something we want, right? If we only do the map estimation, like suppose this is a posterior distribution, right? So it's quite complicated. If you just do the map estimation, you're gonna just find one point in the posterior distribution, which gives the maximum posterior probability density, right? But doesn't cover the whole distribution, right? So the Bayesian world we actually wants to compute the whole distribution of the parameters data given the observed data D. And map estimation only give you one mode of the posterior distribution. So as the semester goes on, you'll see that we actually have a lot of methods to approximate the posterior distribution. Right? So because the posterior distribution is so hard to compute, it's rarely feasible to get the exact form of the posterior distribution. Right? So I have to come out different ways to approximate that. So the major idea is that okay, I'm going to capture those uncertain information over all possible choices of data on the posterior distribution, but not necessarily to capture the very curvature information in this posterior density. That's too hard. That's really too hard. And in most cases, actually, if you can roughly capture the whole information of the uncertainty over the choices of data, that's enough. That's the practically useful things. Okay. If we take a look at the map estimation here, right? So this is essentially a point estimation, right? Sorry, let me actually use argmax data. This is essentially max, of the joint probability of theta and D, right? So, well, if you divide this by D, it doesn't matter, right? Because divided by constants. So map estimation essentially is equivalent to maximize the posterior distribution density, right? So that means, okay, this is your posterior distribution. It might be quite complicated, right? The map estimation only finds one particular value of theta which can maximize the posterior density. You only know one point information here. But from the Bayesian world, right, we want not only this one point, right? We want the whole distribution. Like I want to know, okay, when beta takes different values, how likely is it? Because all those information, we want all those information, not just the choice of data which has maximum possible chance to appear in the posterior distribution. We're looking at whole distribution. It's not just one point. That's from the Bayesian perspective. From probabilistic perspective, what we're seeking for. Good question. Any other question? Okay, great. So now we quickly review maximum likelihood estimation and maximum posterior estimation. Now let's start with the common used probability distributions, right? Again, I want to emphasize that they are used everywhere, all kinds of statistical applications, right? They are building blocks to construct more complex probability models, right? So sometimes, like you see that, deep learning literature, they will like log likelihood, maximum log likelihood estimation over, say, discrete random variables. They call it cross entropy. To me, I really don't like their way, like inventing new terms of that. They're all like maximum likelihood estimation, right? They call it cross entropy. They are building blocks to construct more complex probability models, right? Right. So let us start with binary variables. If I want to use a probability distribution that describe binary variables, which distribution will you come up in your mind? Any thought? Binomial? Not yet. Just one single outcome, which is binary. Bernoulli, right? Bernoulli is just like toss a coin, right? You got heads up, it's 1. You got tail up, it's 0, right? Outcome is either 1 or 0. It's very straightforward. Like, okay, I'm gonna assume, okay, the probability you see 1 is p, right? Oh, is mu, right? And then the probability you see 0 is 1 minus mu, right? Then I can write down the probability distribution, the probability density function as this guy, right? Mu to the power of x times 1 minus mu to the power of minus x, right? Why? Because x is either 1 or 0, right? When x is 1, then probability is mu, right? When x is 0, probability is 1 minus mu, right? The other term is simply 1. Then the expectation of x is what? It's just mu, right? It's just the probability that your variable takes value 1. Right? This is very easy to show that because the expectation is your x takes 1, right? Which is 1 times the probability your x takes 1, which is mu, and x takes 0 times the probability you take 0, which is 1 minus mu, right? 0 times anything 0, so just give you mu, right? And you can apply the same formula, like standard formula, to compute the variance, which is mu times 1 minus mu. It's very simple, but very common used distribution, right, to model binary variable, right? So now come to the question, like, how do we estimate the parameter? So we know that there's only one parameter which can determine this Bernoulli distribution, which is the mu, right? The chance that you see 1. You see the value to be 1, right? So suppose you have collected n ID observations independently, identically distributed observations x1 to xn. Right? How do we do the maximum likelihood estimation of mu? You just write down the likelihood over this n examples, right? Because they are ID, that means the joint likelihood is decomposed as the product of their individual likelihood, right? It's like this, right? And each individual likelihood, as we just mentioned, right? This is a probability density function, which is here you just substitute xn for x, right? So it's mu to the power of xn times 1 minus mu to the power of 1 minus xn. Right? So now if you want to do the maximum likelihood estimation, you just take a logarithm of the likelihood, right? So it ends up with this, right? And now you take the gradient with respect to mu, right? And solve the gradient to be 0, you see that it is actually the average of the n observations. And each observation is either 1 or 0. This guy actually is a ratio of ones, right? Like you have the 10 observations, like 6 of which are ones, the remaining are zeros. Then your maximal likelihood estimation is 6 over 10. Does it make sense? So now we generalize to the so-called binomial distribution, which I mentioned before, right? Like binomial distribution. So binomial distribution is extension in that, okay, I kind of like extend my experiment, right? So my previous experiment is okay, just this torus my current once. I want to see if I say heads up or tails up, right? So now suppose my experiment is that I'm gonna toss a coin for n times, right? Of course, it's independent tossing, right? Independent for n times, right? Then we would like to know how many heads can I see, right? Of course, you might see 0 times, you might see 1 times, you might see n times, right? So you can take the value from 0, 1, 2, 6 until n, right? So there are random variables. We would like to know what is the probability that the number of heads to be 0, 1, 2, 3, 4 until n. Right? So, so we denote this random variable by binomial and parameterized by 2 parameters. One is the n, right? The number of Bernoulli experiments, and second is mu, right? What is the probability of each experiment's outcome is 1, right? And then the probability density that x takes any value, like between 0 and n, is like this, right? So this one, the first one is the combination number, right? If you take from n items, you take x out of it, how many combinations you can choose from it. Right? And for each particular choice of x, right, the probability will be mu to the power of x, and then for the remaining n minus x results, they are observed as 0, right? So their probability is 1 minus mu to the power of n minus x. Right? You need to count like how many different experiments, all of this, all big n experiments will result the same, like x times that you observe 1. Right? So that's why we use this combination number. Right? Okay, this is the definition of combination number. Does it make sense? Yeah, but everyone has seen this before, right? So so you can see that this is a pretty it's pretty straightforward approach. Like you just look at, okay, for a particular sequence of experiment like x, you see once shows up for x time, right? This probability density is mu to the power of x, 1 minus 50 to the power of n minus x, right? That we need to consider all possible sequence of experiments which have the same number of ones. Right? That's why we use combinatorial number here. Right. So how do we compute expectation and variance for the binomial random variable? How can we do that? Of course, you can use this, right? You can use this formula to compute. And now I want to ask you guys to think about a simpler approach. Yes, exactly, right? I believe that you have used this trick before, right? Maybe in your calculus or statistics course before. I just want to stimulate you to think about that, right? So, of course, I can use this formula to compute that, but it's kind of like tedious, right? So, we know that x, right, which is number of the ones. I'm saying that if you denote the outcome of each experiment by, say, x1 to xn, right? So remember, each outcome is binary, either 1 or 0, right? So the finally number of the times you see 1 is simply the summation of x1 to xn, right? Does it make sense? And also x1 to xn are independent because this is definition of a binomial experiment, right? And then our expectation of this guy is expectation of summation of expectation of each individual experimental outcome, right? And for each individual experimental outcome, expectation is simply mu. So you add up n ID experimental outcomes, then the summation is simply n times mu. And similarly, because these random variables are x1 to xn are ID, so the variance of x is summation of the variance of each individual experimental outcome, right? So, okay, and this guy is mu times 1 minus mu. You just add it for n times, so you get n times mu times 1 minus mu. Any questions so far? Okay, great. Let's stop here today. I see you on Thursday. Okay.
I have a question.
Sure.